Hello, and welcome to our channel. With this video, we'll start our journey of probability and statistics in data science. Data science has become one of the most in-demand fields in present times, and to master the data science skills, one must have sound knowledge of probability and statistical methods. Whether it's forecasting stock prices, optimizing the marketing strategies, or predicting user behavior, probability and statistics provide the foundation tools to turn the data into actionable insights. This video series has been created with an aim to enable the learners to build fundamental probability and statistical concepts to establish a solid foundation for data science and apply the theoretical knowledge to devise solutions for various probability and statistics problems with a focus on practical applications. We will also consider several example problems, starting with simpler to more challenging ones throughout the videos to enable you in developing a robust understanding of probability and statistics. With that, let us now start with the basics of probability. It is the branch of mathematics that deals with quantifying or measuring the uncertainty. It basically measures the likelihood of random events. Let us say there is 70% chance of rain tomorrow or 40% chance that you will go out on a trip next month. So, this precision is what makes our predictions meaningful. The statistical or empirical definition of probability says that if in Y trials an event happens X times, then the probability of happening of A will be given as limit of Y tends to infinity X upon Y. Now let us talk about the elements of probability. The first one is random experiment. It is an experiment whose outcome cannot be predicted with certainty. For example, during a coin toss, we cannot predict the outcome of the toss in advance, so it is an example of random experiment. The next element is sample space, which is the set of all possible outcomes of an experiment. Again, in case of a coin toss, the sample space will comprise of a head and a tail, since no other outcome is possible. Next one is an event. It is any subset of the sample space. For example, getting ahead during a toss is an event which is a subset of the sample space, head and tail. Before we go any further, let us look at this table. Here, the symbol in first row is read as union and the second one is read as intersection. The union denotes or condition and requires addition, whereas the intersection denotes and condition and requires multiplication. These are common notations in probability theory. Now, let us talk about the types of events. The first one is exhaustive events, sometimes also known as collectively exhaustive events. It is a set of events that includes all possible events. For example, while rolling a dice one time, we have 6 possible outcomes, which can be anything between 1 and 6. So for one throw of the dice, we have 6 exhaustive events. Let us consider 2 events. Event A and Event B. For these 2 events to be exhaustive, together they shall comprise the sample space. We can say that probability of A union B equals the probability of sample space, and that will be equal to 1 since it comprises all the possible events. Next is mutually exclusive events. Here, if the occurrence of one of the events precludes the occurrence of all other events, such are called mutually exclusive events. In our example of throwing the dice, for once, we are getting only one of the numbers between 1 to 6. So, in case of events A and B to be mutually exclusive, we should have A intersection B as null. Or we can write it as probability of A intersection B equals 0. The next is an independent event where, if the occurrence of one of the events does not change the probability of occurrence of another event. Such are called independent events. Let's consider throwing the dice 2 times. In that case, result of first throw will have no effect on result of second throw. So, we can say that throwing a dice 2 times or throwing 2 dices are independent events. Now, events A and B are independent if we have probability of A intersection B equal to probability of event A multiplied by probability of event B. So, for events A and B to be independent events, it should satisfy this condition. Next is equally likely events. If one of the events cannot be expected to happen in preference to the another. Such are called equally likely events. For example, while throwing a dice, there is an equal chance of getting either of the numbers 1 to 6, or, in another example, while drawing a card from a deck of 52 cards, there is an equal probability of being drawn for all the cards. If we again look at events A and B, so event A and B will be equally likely if the probability of A is equal to probability of event B. Next is complementary events. It represents everything else that can happen besides a specific event. So let us say we denote event A prime as not happening of A. Then, the probability of not happening of A will be 1 minus probability of happening of A. So, this was about the various types of events. Next, we will discuss about the probability axioms. Axioms are the statements that are assumed to be true and therefore they do not require any proof. In probability, we have 3 common axioms. First one is that probability of any event A lies between 0 and 1. The next one is sum of probabilities of all the events is equal to 1. And the third one is for mutually exclusive events, say AI, where I represents 1 to n. The probability of union of mutually exclusive events is equal to sum of probabilities of individual events. Simply, this can be written as for events A1 and A2. Probability of A1 union A2 will be equal to probability of A1 plus probability of A2 for all A1 intersection A2 equal to null. Next, we have the approaches to probability. We have 2 common approaches. The first one is classical approach, which assumes that all the outcomes are equally likely. Mathematically, we represent it as the ratio of number of desired outcomes to the total number of possible outcomes. And the second approach is frequency approach, which assumes that outcomes may not be equally likely. Probability in this case is defined as the relative frequency of occurrence of the events. The frequency approach is more about observing and collecting data. It looks at the real-world frequencies of events. Mathematically, we would represent it as the number of times a specific event occurs to total number of possible events. The classical probability is about the theoretical principles, while the frequency approach is about practical observations. It's like difference between predicting the weather based on models versus looking at the historical weather data and making predictions. Further, we shall discuss underlying concepts of probability in the next video. Meanwhile, please like and subscribe our channel and stay tuned for upcoming videos. Thanks for joining me. I'll see you in the next video.